Hello, welcome to our next topic, which is balancing redox reaction. In the last topic, we have learned how to assign oxidation number. Then we apply that skill in identifying oxidation reaction in a redox reaction. Okay. So in balancing redox reaction or equation, there are several rules a step that we have to follow. First, you find the two elements that changing oxidation number and indicate the total change for each. Then make the gain of the elements equal to the loss of electron by cross-multiplying, and you balance this element on the other side of the equation. Then lastly, to complete the balancing, you have to do it by inspection, and this often include the following. You balance first the remaining metal and then balance your common anion, and followed by balancing the hydrogen and oxygen. To begin with, we are given here an example to balance for redox reaction. Okay, and we follow the rule that we have learned in assigning oxidation number. That element in a combined state the oxidation state is 0. And the sum of that oxidation number in a compound is 0. Okay. So, to begin with the first number, wherein you have ferrous chloride, potassium permanganate, and hydrochloric acid, giving you ferric chloride, potassium chloride, manganese chloride, and water as the product. Okay, last time you have learned to identify which element undergo reduction and oxidation, but we have only 2 reactants there. This time we have 3 reactants forming 3 or more products. So to begin with, let us have the first number. Okay, the first step is we assign oxidation number to each element, both product and reactant. Okay, applying the skill that you have learned previously, here for binary compound, ferrous chloride, chlorine is -1, iron is +2 by the crisscross method. Potassium permanganate, oxygen is -2, potassium under family 1A is +1. Then you have -8 plus 1, that is -7, so this must be +7, so the sum is equal to 0. Again, if we have binary, it's easy. If we have binary compound, we just apply the reverse of the crisscross method that you have learned in writing formula. So hydrogen being family 1A, you have +1, chloride being 7A, -1. Okay, by the crisscross method, you have that. Okay, and it's equal to 0. Again, binary compound, we just apply the reverse of the crisscross method. Ion being ferric, +3, and chloride -1. Then potassium, +1, chloride -1. Again, we have here the binary compound. The 2 here refers to manganese, and chloride under 7A is -1. And water, hydrogen is +1, oxygen is -2. Then the next step, we identify the 2 elements. That is, we are still on the first step. To carry the first step, we should apply the skill that you have learned in assigning oxidation number. Now, we will find the 2 elements that change its oxidation number, and we will indicate the total change for each element. Okay? So, by examining the oxidation number, you will see at once that ion here from +2 to +3. Okay. So, referring to your number line, from +2 to +3, you are moving to the right of the number line. And 1 unit, +2 to +3. So, there is an increase in oxidation state. And when you increase in oxidation state, that means you lost electron. How many? 1. Positive 2 to positive 3. So, there is a loss of 1 electron per atom of iron. And in the compound ferrous chloride, you have 1 atom of iron per mole of ferrous chloride. So there is a total loss of 1 electron per mole of ferrous chloride. Okay, next. We identify the one that gained. If someone lost electron, there must be someone gaining electron. And here we can pinpoint that with your manganese from positive 7 to positive 2. From positive 7 to positive 2, so you're going towards this direction, towards the left side of your number line. So 6, 7, so we have 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. There is a gain of 5 electrons by manganese. So manganese gain 5 electrons per atom of manganese. And in the compound potassium permanganate, you have 1 atom of manganese per mole of potassium permanganate. Okay, so there is a total gain of 5 electrons per mole of potassium permanganate. Okay, the atom cancel out. Similarly here, okay, that gives you the unit per mole. Then the next step, now that we have determined the total chains for each, the next step, oh, by the way, we first identify which is our oxidizing agent from that. From our previous discussion, you have the acronym Leora Geroa. Okay, loss of electron undergo oxidation reaction, and it is the reducing agent. Okay, and the reducing agent and oxidizing agent are found at the reactant side. Okay, so the one that lost electron is the element iron. Okay, so it's undergo oxidation reaction. So the reducing agent is ferrous chloride, okay, where iron is present, okay, because iron undergo oxidation reaction, therefore the reducing agent is the compound in the reactant side, ferrous chloride. On the other hand, when you gain electron, you undergo reduction reaction, and the element that gain electron is the manganese, so it undergo reduction reaction, therefore the compound where manganese is combined as part of the composition of that compound, that is potassium permanganate. That is your oxidizing agent. Okay? Now moving on, then the next step says that you make the gain of electron equal to the loss of electron by cross multiplying. Then you balance that on the other side. Okay? So by cross multiplying, there is 1, meaning you cross multiply the element, then you have 1 would be the coefficient of manganese here. The one that is lost by iron. And the one that is gained, the 5 electron that is gained by manganese, 5. Meaning, 5 iron give off 5 moles of iron, atoms of iron give off 1 per atom 1, 5 electron to manganese. Okay. And 1 electron is lost by iron per atom. So we need 5 atoms of iron, and that is the total gain of manganese. The one ion is losing 5 electrons, 1 each per atom, and only one atom of manganese will satisfy that because it needs 5 electrons per atom. Okay? So that is what we meant by cross multiplying. Okay, we write 1 here to denote that we have just balanced the number of electrons that is gained and lost between iron and manganese. Then the next step, you balance on the other side in terms of this element that changes the oxidation number. Okay, so the 5 here, iron we have 5, we balance on the other side, we have 5. Then manganese, we have 1 here, we balance here, we write 1. Then next step, after doing that, in terms of the element, the two elements that change their oxidation number, we continue balancing by inspection. We complete the balancing by inspection by following the sequence. The remaining metal, the common anion, then hydrogen and oxygen. Okay, the balancing by inspection is done because the remaining elements have not changed. Only the two that undergo the cross multiplying, the two that undergo the loss and gain of electron are cross multiplied. Then the rest who have not changed their oxidation number will be balanced by inspection. Okay, so the remaining metal that has not changed its oxidation number is potassium. We have 1 here, so we write 1 on that to balance that. Okay, next we have the anion, that is the chloride. Okay, on this side, we have chlorine is 5 times 2, we have 10 plus 1 here. On the right side, in terms of chlorine or chloride, we have 5 times 3, we have 15 plus 1. Then we have plus 1 times 2, we have 2, and a total of 18. To balance that on the left side, we have 18 on the right, and we have only 11 here. We cannot change this one because that is part of the first step. So we can only change the coefficient of the untouched compound or molecule. So to balance that, if we multiply this by 8, that will make it a total of 18. And we write it here. Now that we have balanced the chlorine on both sides, next is balanced hydrogen. Okay, because the inspection, the sequence, I said that remaining metal, common anion, then hydrogen and oxygen. So in terms of hydrogen, in this side you have 8. On the right side you have only 2. Okay. To balance the number of hydrogen, we have to multiply this by 4. Okay, to make it 8. Okay, 8. The next is we balance the oxygen. Okay, oxygen is, we have 4 here. And on the other side, oxygen, we have 4. So balance, balance. But you are not allowed to write the coefficient 1. If the coefficient is 1, you don't need to write it. So we have to rewrite. So finally, we have the balance equation. 5 moles. 5 moles of ferrous chloride will react with 1 mole of potassium permanganate, 8 moles of hydrochloric acid, give you 5 moles of ferric chloride, 1 mole of potassium chloride, manganese chloride, 1 mole, and 4 moles of water. Okay, the one here is no more written. Okay. Now moving on to the next number, we have dihydrogen sulfide, potassium permanganate, giving you plus hydrochloric acid, rather, giving you sulfur, potassium chloride, and manganese chloride, and water. Again, assigning oxidation number, the first step to determine which two elements have changed their oxidation state. Okay, here by crisscross method, we have binary compound, so it's easy for us to do the reverse of the crisscross method. Again, we have tertiary compound. Here we have -2, +1. So this must be +7 because we have here -8 plus 1. We have -7 to make it equal to 0. That is +7. So next here we have -1, +1. Sulfur in a combined state is 0. Okay, now we have another binary, +1. Again, another binary, +2, -1. Then -2 for oxygen, +1 for hydrogen. Okay, now we examine which two elements have changed their oxidation number. Obviously here, at one slash, you can see sulfur from -2 to 0. Okay, using your number line, -2 to 0. You are moving to the right of the number line, -2. So you have 2 electrons, the loss of 2 electrons. Because from -2 to T0, you increase your oxidation number. Loss of 2 electrons per atom of sulfur. And there is 1 atom of sulfur per mole of dihydrogen sulfide. So there is a total loss of 2 electrons per mole of dihydrogen sulfide. Okay? Now next, we identify the other element. If there is element that is giving electron, there must be someone accepting that electron that is being given off by sulfur. So here we have manganese from +7 to +2. From +7 to +2, that is gain of 5 electron, 5 units in the number line, that is corresponding to 5 electron per atom of manganese. And since you have 1 atom of manganese per mole of potassium permanganate, so there is a total gain of 5 electrons per mole of potassium permanganate. Okay. Now that we have identified the two elements that lost electron and that gain electron, first we identify which is your oxidizing agent. Again, the oxidizing and reducing agent is found at the reactant side. Okay, using our cue card, when you lost electron, you undergo oxidation reaction, and that is the reducing agent. The one that lost electron is sulfur, and it is in the compound dihydrogen sulfide. So the reducing agent is dihydrogen sulfide. Okay, now the one that gained electron is the manganese. So the oxidizing agent is potassium permanganate. Okay. Now next the next step is we multiply. We cross multiply the two elements that gain and loss, the loss and gain of electron. So that means the 5 that is gained by manganese is coming from sulfur. So we multiply sulfur here at the start of 5 and the manganese by 2 here. Then after cross multiplying, that means that you have 5 here, 5 sulfur. Atoms of sulfur will lose 2 electrons per each atom, so there is a total 10 electron that is lost by sulfur. Okay, in this case, manganese, 2 atoms of manganese, each atom will receive 5 electrons, and that is 10. So as the sulfur give off 10 electrons, 2 atoms of manganese, 5 atoms of sulfur, 2 atoms of manganese satisfy that 10 electron that is lost by sulfur. 5 atoms of sulfur, 2 atoms 5 moles rather, where 2 atoms per 2 electron per atoms is given off by sulfur. Okay, so you have 2 atoms off. Okay, now to balance that on the other side, you have sulfur 5, we have sulfur 5 here, and manganese 2, so we write 2. Okay, the next step, now that we have cross multiply and balance on the other side as well, the next step is complete the balancing by inspection. If there is any remaining metal, then common anion, then hydrogen and oxygen. So the remaining metal is potassium. Okay, we have here potassium 2, we have here 1, so we write 2 here to balance the potassium. Then the remaining anion is chlorine or the chloride. Okay, in this side, okay, we balance chloride 1. On the others, on the right side, you have the chloride ion. You have here 2 plus, you have 4. Okay, so this is a total of 6 electrons. Okay, and here we multiply this by 6 in the start of the formula to balance the number of chlorine. That will give you 6. The next step is you balance hydrogen. Okay, from hydrogen, here we have 10 from the hydrogen sulfide plus 6 from hydrochloric acid. In this side, we have only 2. So we have a total of 16 here. So we multiply this by 8 to make it 16. So we write it as start of the molecule. Then next we balance oxygen. We have 2 times 4, that gives you 8. And oxygen in this side is 8. So balance, balance, balance. Okay. So we have now we rewrite the final equation as 5 moles of dihydrogen sulfide and 2 moles of potassium permanganate and 6 moles of hydrochloric acid will give you 5 moles of sulfur, 2 moles of potassium chloride, 2 moles of manganese chloride, and 8 moles of water. Okay? Next number, for the third number, we have your potassium dichromate and sulfur. That is the elemental state of the sulfur in a crystal structure, S8, giving you potassium oxide, chromium oxide, and sulfur dioxide. Again, we assign, first step, we assign the oxidation number to determine which 2 elements have changed their oxidation number. Again, we have here potassium under family 1A is positive 1. Oxygen is always negative 2 except in peroxide. So applying the rule that the sum of all the oxidation number in a compound must be equal to 0 or oxidation. So we have negative 14 here plus 2. We have negative 12 divided by 2, negative 6. So this must be positive 6 to make it equal to 0. So positive 2 plus 12 is positive 14 plus negative 14, 0. Sulfur here is 0 because it is not combined with any other element. Okay. Then, moving on, we have oxygen negative 2, potassium being on family 1A positive 1. Again, this is by crisscross method. Oxygen is negative 2, chromium is positive 3. So oxygen is negative 2, so sulfur here must be positive 4 to make it equal to 0. Now, identifying the 2 elements that change their oxidation state, You have here, obviously, you have here sulfur. Okay, from 0 to positive 4. Now, referring to your number line, from 0 to positive 4, you're going this direction to the right. So, you have 4 units or 4 electrons. So, there is loss of 4 electrons per atom of sulfur. But in this molecule, you have 8 atoms of sulfur per mole of that crystal structure of sulfur S8. So there is a total loss of 4 times 8, 32 electron per mole of the molecule S8. Okay? The crystal state. Next, we have your element that change state is chromium from positive 6 to positive 3. Positive 6 to positive 3, you're going into the left of your number line. So you move 3 units. So there is a gain of 3 electrons per atom of chromium. And in the compound potassium dichromate, you have 2 atoms of chromium per mole of potassium dichromate. So there is a total gain. 2 times 3, you have of 6 electrons per mole of potassium dichromate. Okay. Now, we identify which undergo oxidation and reduction and identify the reducing and the oxidizing agent. Okay. Using again the chart. If you lost electron, you undergo oxidation reaction and it is the reducing agent. So the reducing agent is the sulfur crystal. Okay? If you gain electron, you undergo reduction reaction and that is the oxidizing agent. So it is the potassium dichromate where chromium is part of it. The element that is reduced is chromium. But the oxidizing agent is the whole compound where it belongs. That is the potassium dichromate. Here it is uncombined, so it is just simply the sulfur crystal. Okay, moving on. Then the next step is we cross multiply. However, you will observe that you have 32 is to 6 is the one that you have to cross multiply. We have 32 is to 6 that can be reduced to 16 to 3. Okay, that 16 is the one that is lost. So that would be the coefficient of chromium. Okay, so you have here chromium 16. Okay, the one that lost and the one that gained chromium. So the gain must be the coefficient of sulfur that is here 3. Now that we have cross multiply it, let's just examine in terms of the element that is reduced and oxidized. Okay, sulfur here, 3 atoms of sulfur, 3 moles rather, of sulfur. And per atom of sulfur is giving 4 electrons. Okay. Yan. And you have 8 there. Here in this case, for every atom of chromium, it gained 3 electrons. And you have 16 times 2. You have 32. Then you have 24. 3 moles. And each atom of sulfur is losing 4 electrons. So that is, you have 8 atoms there. You have 32 times. Okay, that is how we cross why we have to cross multiply it. Okay. Now, moving on. You have 3 times 2, 6 times 16. Okay, yun ang kanyang, it will gain that much. Okay, here you have 4 times 8. You have 32 times 3. Okay. Now, again, after cross multiplying, we balance on the other side. You have here sulfur 3 times 8, we have 24. We have to write 24 here because we have only one sulfur. And in terms of chromium, you have 32. So we have also 16 here. The next step, we balance the remaining metal, which is potassium. So we add 16 here as well. Okay. We don't have an ion. So we don't have hydrogen. So the next is oxygen. So we have oxygen here, 7 times 16, that is 112. On the other side, oxygen is 16 plus 48 plus 48. And that gives you 112. So balance, balance. So we have the balance equation, 16 moles of potassium dichromate will satisfy 8 moles of sulfur 8, giving you the product 16 moles of potassium oxide, 16 moles of chromium oxide, and 24 moles of sulfur dioxide. Okay, moving on to the fourth number, we have copper and nitric acid. Okay, again, the first step is to assign oxidation number 0 and combine -2 for oxygen, +1 for hydrogen. Applying your crisscross method, you have -6 plus 1. This must be +5. Then the 2 here, by the crisscross method technique that you have learned in writing formula, that corresponds to the oxidation state of copper. Okay, oxygen is always -2. So we solve that. You have 3 times 2, 6 times -2, you have -12. -12 plus 2, you have -10. You divide that by 2, that is -5. So that must be +5 to make the total equal to 0. So we have -2 times 6, we have -12 plus 10, -2 plus 2, 0. Okay, next we have -2 plus 2. We have here -2 plus 1. Now, examine carefully which two elements change oxidation number. Obviously, you have pinpoint here, you have your copper from 0 to +2. From 0 to +2, that is loss of 2 electrons per mole of copper. Okay, that is the total loss. Then you will observe that in this case, there are some nitrate that don't change nitrogen in the nitrate. There is no change in oxidation number in that case. However, some of the nitrogen from the nitrate here change its oxidation number to +2. So from +5 to +2, there is gain of what? From +5 to +2, there you gain how many? +5 to +2, you have 3 electrons per atom of nitrogen. and there is one atom of nitrogen per mole of nitric acid. Okay, so you gain 3 electrons per mole of nitric acid. Okay, when you have that case that some of the nitrate is still nitrate going out in the product side, but some of the nitrate is going out as N2 in the product side. So before we can balance that, we cross multiply, we should split the two first and identify which one is not changing and which one undergoes the reduction reaction. Okay, again, we identify first which is our oxidizing agent. Again, the oxidizing agent is the one that gain electron. The one that gain electron is the nitrogen in the nitric acid. So your answer must be some, not all. Some of the nitric acid is the oxidizing agent because some of the nitric acid doesn't change its oxidation number here. Only some, not all of them. Okay? Then the reducing agent, the one that lost electron, therefore it is the copper element. Okay, as one of the reactant. So, to balance that, we have here, we rewrite the equation. So, we identify this nitrate and that nitrate, no change. Because only some of the nitrate change. So, when we adjust the coefficient here of that nitrogen, only this one will be adjusted, not this one. Because that is an ion and that undergoes no change in oxidation number. Now, next step, we cross multiply. So, the 2 here that is lost by copper will be gained by the nitrogen. So, we have 2 in this one. Okay. So, when we change the coefficient, the number of nitrogen here, we have to balance it here as well. We don't do that. We don't change this one because that is for the no change in oxidation number. Then the 3 will be the coefficient of copper here. So we write copper there. Okay, next, there is no remaining metal, but we have an ion, nitrate here, and nitrate. That is not changed. Okay, so balancing that, we have just make the balance of the 2 electrons that change oxidation number, then followed by metal. We don't have a metal. Then we have an ion nitrate. Here in this side, the nitrate NO3 is 1. On the other side, you have the nitrate ion. Here, we have 3 times 2. You have a total of 6. So, if you multiply this by 6, you don't do it this way, but you attach it at the beginning of the molecule. So, that is 6. So, balance. Then, after the anion, we balance the hydrogen. Okay, the total hydrogen on this side, we have 2. Then, plus 6. That will give you 8. On this, on the other side, the hydrogen is 2. So, to make it balance on the left side, we multiply this by 4. So, we have it here, balance. Then next, we have oxygen. We have oxygen, we have 6 plus 18 here. 6 times 3, 18. 2 times 3, 6. And that gives you 24. On the other side, for oxygen, you have here, 6 times 3, that is 18. Okay, 9 times 2 plus 2 plus 4. And that gives you 24. Okay, balance. Okay, but you cannot leave it this way. So, finally, we sum up that. The one that undergoes oxidation, a reduction by the way, and the one that doesn't undergo. So, totally, we have 3 moles, 3 atoms of copper, 2 plus 6, 8 moles of nitric acid, then 3 moles of copper nitrate or cupric nitrate, and 2 moles of nitrogen oxide, and 4 moles of water. Okay. I guess that's all for balancing redox equation at this point. I hope you have gained a skill in balancing redox equation.